Okay, our goal in this video is to find the surface area of a parameterized surface. So I need to go over a definition first, and that is a surface parameterization R is smooth on a set D, which is an R2, if RU cross RV is not equal to 0 at all points in D. So what this means is that RU and RV are not parallel to each other ever, but let's think about what would happen if they were parallel to each other. That means the surface parameterization would not really be parameterizing a surface at that point, it would be parameterizing a one-dimensional object at that point, because the surface parameterization is kind of going in the same direction regardless of which direction you're going on in the domain. Okay, so like I said, our goal is to say we have S, which is parameterized smoothly by R, which goes from D happening in R2 to R3, and also we need this thing to be one-to-one. Otherwise we'll be double counting part of the surface as we do the calculation for area, and our goal is to find the area of the surface, so I'll call that A of S. So I've written up here how we're going to do this, what the idea will be, and I've put a brief sketch also because I can't sketch this in real time very quickly. So the idea goes like this. We want to approximate S by parallelograms, and what those will really be are just portions of the tangent plane at a certain point. So just a bunch of little portions of tangent planes, and then we'll find the area of all of those parallelograms, sum all of those areas up, and then finally take the limit as the number of parallelograms goes to infinity, but that's going to turn something like a Riemann sum into a double integral. Okay, so here's my picture. So I've got my region D over here, which is outlined in yellow, and then what I can do is, regardless of how funky the shape D is, I can approximate the shape D first by rectangles. So I've made these rectangles over here pink. And then what we want to do is look at what's happening to one kind of representative rectangle inside of this D. And so this is the ith rectangle in the u direction and the jth component in the v direction. So this is like the ij rectangle right here. And it has a point coming from it, ui star, v, j star. And then what's happening is that this whole picture is being mapped over there into R3 into this cap. So this is like a surface here that this patch over here in R2 is being bent over here into this surface in R3. And what we want to do is look at what's happening to this little rectangle. So this little rectangle will be a little patch of a rectangle over here on the surface. But we don't want to find the exact area of the patch which goes over here to this surface, because if we could do that, then we can find the surface area already. We want to approximate the area of the image of this patch. So I've done that by taking this patch over here and approximated its image by this parallelogram. So I want to point out that this point right here, maybe we'll call this point Pij. So this point Pij is R evaluated at ui star, comma vj star. Okay. So this point Pij is serving as like the foundation of our parallelogram over here. Okay, good. And then what we want to do is recall that the area of a parallelogram can be given by the cross product of the vectors that define it. So notice that a vector in one of the directions that will define it is going to be RU. In other words, the partial derivative of R with respect to U. And then the vector that's defining it in the other direction will be RV. And you might think, well, what is the length of those vectors? Well, the length of those vectors in the RU direction is delta U, because here we'll say that this distance right here between this vertical line and this vertical line, in other words, the width of this rectangle, we'll call that delta U. So I won't write it in there because it'll get messy, but this width right here is delta U. And then in the v direction, the length of this thing is delta v for the same reason. This height of this rectangle is delta v. Okay, so from all of this, what we can say is that the area of Sij. So we'll say Sij is that parallelogram right there. So the area of this parallelogram is given by delta U, R U, evaluated at Ui star Vj star, crossed with delta V, RV, evaluated at Ui star Vj star. Great. But now what we can do there is, oh, and sorry, it's not the cross product, it's the magnitude of the cross product. But now what we can do is take the U and V out, I should say the delta U and the delta V out, so that makes the area of this parallelogram equal to the magnitude of RU, Ui star Vj star, cross RV, Ui star Vj star, and then I'm taking my delta U and my delta V out. We're assuming delta U and delta V are positive, and so we can do that. They're all automatically scalars. Okay, so the next thing that we can do is say that the area of our entire surface is going to be equal to, well, it'll be the sum of these, and then we take the limit. So here I'll say the limit of the sum of these ASIJ, and here we're summing over I and J. So that's what we get for this area. Just kind of like a super general version of a Riemann sum from Calculus 1. But now, looking at the shape of this guy right here, it's pretty obvious that this is going to give us exactly the double integral over D of the magnitude of RU cross RV dA. Okay, and that's exactly what we get. So this is our surface area formula. Okay, so what I'll do is I'll put that surface area formula over here, and then we'll run through an example. Okay, so on the last board, we argued that we have the following formula for the area of a parametric surface. So if it's parameterized by this function r, whose domain is D, then we get the area of that surface is the double integral over D of the magnitude of RU cross RV dA. Okay, so now what we want to do is find the surface area of a sphere of radius r. So, I mean, this is a good example because we can just look in a textbook what the surface area of a sphere of radius r is. And so this just checks that this whole system works. Okay, so first of all, we need to parameterize a sphere of radius r. So just like we've done before, we want to take inspiration by spherical coordinates. And so let's just recall spherical coordinates are given by rho cosine theta sine phi, y is equal to rho sine theta sine phi, and then finally z is equal to rho of cosine phi. Okay, but in this case, what we want to do is set rho equal to this r, which is fixed. Now, generally, spherical coordinates will give you the entire 3 space, but we want to stop that at a sphere of radius r. So we'll set rho equal to r, which means our function that parameterizes the sphere can be given by r, which is a function of theta and phi, and it will be r cosine theta sine phi, r sine theta sine phi, and then finally r cosine phi. So we've got something like that. Okay, fantastic. And then another thing to notice is that we have theta going between 0 and 2 pi, and we have phi going between 0 and pi in order to draw the entire sphere. Okay, so now let's go ahead and calculate these partial derivatives. So the derivative of r with respect to theta is going to be minus r sine theta sine phi, and then r cosine theta sine phi, and then 0, because there's no theta over there. And then let's see, r of phi is going to be equal to r cos theta cos phi, r sine theta cos phi, and then finally minus r sine phi. Okay, great. But now what we need to do is cross product these things. So we need to take r theta cross r phi. So let's see, that's going to be in the I component of each one. So we're going to have minus r sine theta sine phi. Then we'll have r cosine theta cosine phi. So that's what we have down there. And then here in the j component, we'll have r cosine theta sine phi, and then r sine theta cosine phi. And then in the k component, we'll have 0 and then minus r sine phi. All right. So that's what we get for this cross product. Okay, so since we're running out of room, I'm going to bring that up to the top and then we're going to start finishing it off. Okay, on the last board we parameterized a sphere of radius r, and we found the partial with respect to theta and the partial with respect to phi, and we set up the cross product. Notice we're working towards this surface area formula which we derived earlier in the video. Okay, so let's go ahead and calculate this cross product. So let's look into the I direction, in other words the first component. So that will be given by taking cofactor expansion with the first row and the first column. So notice that's going to give us r squared, and then cosine theta, and then times sine squared phi, and notice it's negative because we have this minus sign here. And then it'll be minus 0 times this, but 0 times that is obviously 0, so we're good to go there. Then comma, and then for our second component, we need to look at what we get when we cross out the second row and the first column. So here we're going to get, let's see, it's going to be minus r and minus r give us positive r squared, but then there's a built-in minus sign into this part. And so we'll get r squared sine theta, and then sine squared phi. So that's what we get for the second component. Now let's go ahead and look into the third component. So we'll get that from cofactor expansion with the first row and the third column. So notice that's going to give us minus r squared, and then we have sine squared theta, sine phi, cosine phi. So that'll be that product. And from that, we're going to subtract this times this. So that's going to be another minus r squared. And now we have cosine squared theta, and then sine phi cosine phi. So notice that whole second thing simplifies because we have r squared sine phi cosine phi, r squared sine phi cosine phi, but this first one is multiplied by sine squared theta and the second one by cosine squared theta, and sine squared plus cosine squared is 1. So that makes this whole thing a negative r squared sine phi cosine phi. Great. Now the next thing we need to do is find the magnitude of this, because that's what goes here. So let's go ahead and do that. So the magnitude of r theta cross r phi. So recall that's just the square root of the sum of the squares of the components. So that's going to be the square root of this component squared. So that's going to give us r to the fourth cosine squared theta sine to the fourth phi. That's what we get there. And here we have this is plus r to the fourth sine squared theta sine to the fourth phi. So that's what we get for that second one. And then finally plus r to the fourth sine squared phi cosine squared phi. Okay, so we've got something like that going on. But now notice that first of all we have an r to the fourth in all of the terms. So we can go ahead and pull a square root of r to the fourth out. In other words, an r squared out. And then left on the inside, we've got the square root of a bunch of stuff. So let's look at these first two terms. So these first two terms both have a sign to the fourth component, but one of them has a cosine squared and one of them has a sine squared. And then we can use the fact that sine squared plus cosine squared is 1. So that's going to give us a sine to the fourth phi from these first two terms. Good. And then notice the second term is going to be plus sine squared phi cosine squared phi. So we've got something like that. Okay, but the next thing that we can do is notice that this equals sine squared phi times sine squared phi. So that means we can take a sine squared phi out of the whole thing and make it the absolute value of sine squared phi. But we don't need an absolute value because phi is only going from 0 to pi and sine is non-negative there. So that's going to give us r squared sine of phi, and then left under the radical will be one left over sine squared, and then this cosine squared. So what we've done is we've taken out this sine squared and this sine squared. So we've got a sine squared phi plus a cosine squared phi left, but those add up to 1, which means we get r squared sine phi. So that is our r theta cross r phi is r squared sine phi, which is a good place to be because now we can go ahead and plug that into our formula and we're pretty much done. Okay, so on the last board we calculated this magnitude of the cross product of r theta with r phi, being motivated by this formula that we derived earlier in the video, and we calculated that that cross product was r squared times sine phi. And so that allows us to write this area of the sphere of radius capital R as this double integral. The theta integral is going from 0 to 2 pi, the phi integral from 0 to pi of our r squared sine phi. And notice that that is the region described by D here. Okay, but this is a product, so r squared is a constant, and then we can think of this as a product of a theta function and a phi function. The theta function is just the constant 1, so we can write this as r squared times the integral from 0 to 2 pi d theta times the integral from 0 to pi of sine phi d phi. But now we can take the antiderivative of both parts, so this is going to give us r squared. This part very clearly gives us 2 pi. Then the antiderivative of sine is negative cosine phi. We're evaluating that from 0 to pi. I'm going to put these in parentheses so it looks like multiplication and not subtraction. Now what I'm going to do is take this minus sign, change it into a plus by changing the bounds of evaluation. And then we have cosine of 0, which is 1, minus cosine of pi, which is negative 1. So we have 1 minus negative 1, which is obviously 2, multiplied by that 2 gives us 4 pi capital R squared, which is a well-known formula for the surface area. Okay, I'm going to erase the board and then run through one quick example. Okay, for our last example, we want to throw this back to a function. Okay, for our last example, we want to throw this back to a surface which is defined as a function of x and y. So in other words, we want to find the surface area of the surface z equals f of xy where x and y are in D. So like we did in a previous video, this has a nice parameterization where we can just use x and y as the parameters. So x is the first coordinate, y is the second coordinate, and f of xy is the third coordinate. And that's because, well, every point on this can be given by x comma y comma f of xy. Great. But now we need to calculate these partials, but that'll be r sub x and r sub y. So notice that r sub x is going to be 1, 0, and then I'll just write f sub x, so the partial with respect to x. And then r sub y is going to be equal to 0, 1, and then f sub y. Now, taking the cross product of those, so rx cross ry, So that is going to be, we've got in the I component, we're going to have 1, 0. In the j component, we'll have 0, 1. And in the k component, we will have f sub x, f sub y, like that. Okay, so let's see what we get. In the first component of this, we get that from crossing out the first row in the first column. So notice that's going to be minus the partial derivative with respect to x from cofactor expansion. In the second component, crossing out the second row and the first column, we're going to get minus the partial with respect to y. Remember, there's a built-in minus sign in the derivative. And then for the third component, we're going to get just the number 1. Okay, but now we can find the area of this surface is going to be the double integral over d of the magnitude of this guy. But the magnitude of this guy is pretty easy to calculate. Notice that's just the square root of the derivative with respect to x squared plus the derivative with respect to y squared plus 1. Great. And now we've got a nice surface area formula for surfaces of the form z equals f of xy. This is a good place to stop.